Hello. OK. D'abord, bonsoir. Je suis très content d'être de retour ici après 15 ans de partie de Paris. Je retrouve des visages très familiers. Georges, Loïc et autres. Je faisais partie du groupe Hafner C++ avant de partir aux États-Unis. Et c'est la première fois en fait, que je reviens en France pour faire un exposé sur C++. Donc, je suis très content. Donc, aujourd'hui, je vais parler des modules C++. Switching to English. They are coming. So what I would like you to take out of this talk is, first, what are they? They are not white knights, white workers. Why we're doing C++, we're messing with C++ and with modules, and how you should be prepared to use them. And then I'll conclude with a call to action, what you can start doing just now before they become official in next year, hopefully. When I moved from academia to Microsoft, that was 2014, the company at the time was also transitioning from closed source to open source. And they were very much interested in having a robust support for C++. Remember, they had Windows Vista. It was exceedingly successful. Sorry. Then they switched back to C++, and they really wanted to have robust support for C++. The first thing I discovered there was that the Windows source code base is huge. Okay, I know there are some other companies down there in the Silicon Valley, and they say X size code base. Windows is much, much bigger. And handling C++ at that scale is a real challenge. I know Visual C++ has a reputation. It's like somehow it should be against Geneva Convention or something. But it manages to compile Windows source code base, okay? And how we get that done is black magic. I won't get into that. But what they needed is a good support for C++. And they can't do the revolution they wanted to do with Windows without actually having software, language support for software architecture. I was working on generic programming before moving to Microsoft, and I thought the next challenge for programming at scale was to design a module system for C++. So the work I did there on modules was inspired by the huge challenge that the company was facing. But if I had been employed by Facebook, Google, or Red Hat, I think I would have made the same design choices. The only thing that impacted the work I did on modules was just the scale, not the language design choices. Okay, I was given enough resource and freedom to care mostly only about the C++ community and not too much about the other distractions that go in the house. And I'm actually very grateful for that I could work for C++ community and not being constrained by some sheets in the Windows code base. I started with the module TS that you're all familiar with. And during the development, got a lot of feedback, in particular from the Google folks. They too have been working on having some modular supports in C++. and they control Clang. So Clang also had some notion of modules that was introduced by Apple, primarily Doug Greger, who used to work on C++. Now he's one of the lead designers of Swift at Apple, right? Doug was working on modules until 2012, and then nothing happened after that. So in 2014, I took over and proposed a completely different design. And we got a module TS technical specification published, and then we amended again to get it into the working draft. So the reason why you should know about it and care about modules is that they are now in the C++20 working draft. So this is not science fiction, unless getting some major roadblock. This is going to happen. Okay, it's not science fiction. And you can start testing them today. You have at least 3 independent implementations from 3 different compilers. The Microsoft compiler, I did the initial implementation, and since I was overworked, I got help from the team now. The only thing I handle on that is the design and some other stuff. I no longer write the code, but the original code till 2017 was done by me. The GNU compiler, which I used to work on, has an implementation, and the work is done funded by Facebook because they too are interested in modules, compiling at scale. And of course, Clang, because they have been doing this kind of stuff very early on. So if you have to go just now, this is all you need to know. Okay. So what are modules? The way I think about module is that a module is essentially a language support for architectural problems. So essentially, you have a component, and you have a well-defined interface that says, if you're going to depend on this component, these are the entry points and nothing else. Everything else is shielded, is implementation detail. And I promise that if you depend only on those things, I'm going to give you the semantics that I promised. This is very different from header file situations we have today. One of the problems we have C++ is that, if you want to use modern C++, it has to be template. And template live nowhere other than in the header files. And once in the header files, implementation details also leak into users. And that's not good for anybody, for various reasons. So a module has a well-defined interface, and then it can have many independent source files that are just implementations of the interface, and these things, we call them implementation units. And you can name your modules, okay? And the modules can also take dependencies on other components by using symbolic name through import declaration. We'll see that very shortly. So here, for example, I say, well, my module's name is my fancy module. That dot notation currently is just symbolic. It doesn't have any fundamental meaning other than designating a module. So it doesn't give you any hierarchy in the component in any form, okay? It's just symbolic. By deliberate design decision, I didn't want to put any hierarchy into the meaning. I know some people don't like it. I actually think this is a feature. So here is an example of production and consumption of modules. So the syntax I'm using here is the syntax that is in the current working draft. It is slightly different from the syntax that was in the module TS, but not that much, right? So it starts with module semicolon. That used not to be in the TS, now in the working draft, that's what you get. Anything else just look like in the module TS. So if you give this to GCC or Clang or MSVC, it will compile just fine. So the things that are new is you have module semicolon. That's just telling the compiler, oh, this source file is going to use module construct. In particular, it's going to export or do something. Then you have the usual includes, right? And include IO streams, include string, because I'm going to use component from there. And the next line is also new. It says exports module calendar date. So this is the first new thing. It says that this source file is going to define the interface of the module calendar.date. Then it opens a namespace and then exports a class that's named date. So the export keyword was introduced in C++ 98 for what we called exported templates. Unfortunately, they didn't work the way they were intended or designed, and there was only one compiler that implemented exports. So it wasn't widely used, and eventually it was removed. Exported templates were removed from C++ 11, but the words exports were still kept as reserved as a keyword, so all I'm doing here is just reuse it, but I think I'm reusing it in the way it was originally intended, in the good way it was originally intended. So the meaning of this declaration is that the class date is exported. You can use it from the outside to create any object that you want, and further down have two declarations in the export functions declaration, so an operator and a normal function called toString. On the right side, useDate.cxx is a source file that is using the module calendar.date. Again, it starts with include iostream, and then it says import calendar.date. So import in a module TS is a keyword. In the working draft, it is a context-sensitive keyword because people complained about taking the word import. It is so beautiful that everybody has been using it for various reasons. But since we already had exports, there is no way I'm going to use a different word than import. There's symmetry, right? People proposed hash import, and it's like, no way, this is not the preprocessor stuff. It's real language, so we can't have hash anything. And other than that, the rest of the program looks like normal C++ program, right? One of the design principles I had working on modules was that ideally, you shouldn't even see that you're using modules, right? Usually, when we have new features in C++, people scream for loud keywords, syntax. And then after a while, they start cursing the inventor of those syntaxes, like, why are you making me write this stuff? It is obvious, right? An example of that is constexpr. So when I originally proposed constexpr, I didn't have, constexpr compile time functions. There was no keyword constexpr because, it's obvious how it should work. But the compiler writers, they demanded a keyword. So that was the first time that compiler writers actually wanted a keyword. Usually they are the ones screaming against keywords. I was okay, you can have one if you want to, just tell me. And they say constexpr, I say fine. Now these days, almost everything is constexpr. And people are screaming at me and say, why do you make me write constexpr when it is obvious? I write that more than anything else. Like, yeah, I am with you, but I had no choice, okay? If it was me, we would be using export very sparingly, but I didn't have a choice. Again, people wanted it. It's allowed syntax, and this is what we have. But anyway, when you're consuming modules, the syntax is very minimal, and if you just replace the include with import, you're just fine, right? Here is another way of writing the same thing. Okay, sorry. Something is wrong. Oh, yeah. So on these slides, instead of repeating exports, let me show the previous slide again. I had 3 exported declarations in there on a class and 2 functions, right? And namespace, nothing in there. Now, this slide actually move exports in front of the namespace. What that syntax is saying, it is just a shortcut for the previous one. All it is saying is that between the opening brace and closing brace, everything is there is also exported, just shortcut, okay? You're done. So this was essentially what was in the modules TS. when we got feedback, in particular, we wanted to merge into the working draft. We get a lot of resistance from the Google folks because they have different ideas about how things should work. And they proposed what they called header units. I'll get into that later, but this is what it would look like. On the previous slide, I have hash includes. You replace hash includes with imports. Right? You still have the header brackets. And how this works is far more complex than what it looks. And I'll get into details much later. But essentially, what it allows you is to write code that almost looks like if you're writing Python, if you squint right, you have export and you have a bunch of imports and so forth. And you have no hash includes. So somehow this is a way of saying, look, no hash includes, hashtags are passé or something like that. Just to recap, the way I look at modules, I know there are a lot of people who have their own views of what modules are. From the way I look at it, what was the original motivation is that I needed to solve a software architecture problem. The view is that once you bring structure into your assets, software assets, now you can think about making compilation go faster. It is easier to optimize a correct program than fix an incorrect optimized program. The same goes for the software component. I think I can say this. So as I was working on this, I was also having some people in the Windows division. So I work in the developer division, which you can think of as a completely different company. And then Windows division is a different company. So get people using the compiler, experimental compiler going on, especially the people in the Edge, Microsoft Edge team. They were interested in renovating or rejuvenating, whatever you want to call it, their code base. One of the problems they had was that everything was kind of entangled, right? The thought that they had about roughly 90 components, different components in Edge. Probably not the right, but right order. And then they tried to create dependencies between those components so that they can actually have a layered system. So they did the work, computed the strongly connected components. And then they came out, they came out with exactly one strongly connected component. And there were a bunch of cyclic dependencies. It was a nightmare. They couldn't, put structure into these things. So they're very much hung on to having language support for componentization. Build throughput, we'll take care of that later. Okay. The other thing is isolation. What I mean here primarily is macro isolation. If you love macros, then think again. So this is not coming from blind religion or something. This is after having tried for more than 20 years to bring developer tools to the community. You cannot make sense of a source file without knowing the set of all macros that are needed to compile a source file. The way you make sense of a source file is first get it through a compiler. You can't parse C++ without knowing the full set of macros. If you want to have IntelliSense or have your IDE help you, you can't get that done if you don't have all the macros. It is insane. It also means that reusing components is very hard because you have to know the right set of macros. It's just mind-boggling. Okay. So build throughput comes after you get some structure into your software. So you know where things are, who is depending on what, and what you need to really, where you need to really spend your calories, to make things go faster. And the other thing is, I don't know, if people running Java or C# they look at C++ developers and laugh at me because they have ideas, they have a lot of advanced semantics-aware, development tools. And in C++, because we don't have them, we don't know what we are missing, right? Then we tell people, you need developer tools, like, what is that? Like, let me show you. And then you start showing them, what you can do in Java and C#. And say, oh, yeah, but that is C#, that is Python. No. This is what I'm telling you. Oh, I can do that. Yes, you can do that, right? I can do refactoring. To do refactoring, you need the compiler to understand what is going on. You need rich type system, right? You need how things talk to each other. And the other thing that I didn't want to do is to go on some kind of blind crusade trying to replace the preprocessor. That's not going to happen. That will fail. The reason is very simple. The preprocessor has been there for more than 40 years, and it has seen creative usage. You can't think, if you believe you know exactly how the preprocessor is used, then you haven't seen the preprocessor in use. It's mind-boggling what people can do, how unstructured it is. There is no structure. You can't do anything about it. So I did not want to replace the preprocessor. What I wanted is to minimize its usage, minimize needs for the preprocessor. Not replace it, just minimize it so that we can take care of the bigger stuff. For the working programmer, the thing you need to know is that if you have well-developed modules, then you shouldn't worry about macros. Today, if you're developing libraries, you have header files, and you have to think about someone defining these macros or that. No. You don't need to worry about that. The reason is, if someone is using your module through the modular interface, the import, right, their macros is not affecting your components in any form. Similarly, if you happen to use macros, your interface in any way, they are not affecting the guy who is using your module. So you have that complete isolation. It's an impermeable boundary, around the interface and implementation. Also, we have this notion of one definition rule in C++ that we love so dearly. It's at the foundation of anything that we do in C++. With modules, with the design principle that I use, you get ODR, the one definition rule, for free. Today, compilers, when you want to do anything advanced like link time optimization, they also have to check whether things are consistent or not. And that takes a lot of time checking these things, right? With modules, because there is only one place where you can export an entity, the notion that it is defined once just comes for free. You don't have to check for it. If you don't have to check for it, it goes faster, right? Originally, I decided that to be successful, we shouldn't add any new name lookup rules, okay? That was my mantra for 5 years. And I was defeated last year. When I started, I asked the core working group, the place where you find compiler writers, the people who have been there since the beginning, you know all the rules by heart. How many name lookup rules do we have? I never got a right answer. I think if there were 12 people in the room, you'd probably get 15 answers. And at the end, Biane concluded that we must have something like 14.5 rules. I said, .5 rules? Yeah, just to make sure that, we didn't forget about something. So we added some new rules, but for most of the time, you don't need to worry about them. And the reason we need the new rule is templates, turns out. And modules, they do not replace header files. I'm not suggesting that if you have a well-defined header file in your software, you should go and turn everything into module. If you have time for that, fine. If you don't, then we have other ways of getting that. But if you're writing new components, I highly encourage you to adopt modules. It will make your life much easier, and you'll be thankful for that. You thank yourself for that. There are stuff that are just macro heavies, right? If you use Unix, if you use unistd.h, this is one of those header files. Every time you define new macros, you get a bunch of new tokens coming out of it. Windows.h works. Okay, and everybody has one of these things. If you've been there for a long time, you have one of those header files that just spew more tokens every time you add more macros. And really, build time will be faster. This is a promise that we're keeping. Okay. So, if you're going to use modules, what are you going to do? My suggestion, and there are a lot of people who have opinions, but my suggestion is, since include files are not going away, something like assert.h is definitely not a module. It is not a candidate for modules. The reason is very simple. If you define and debug, you act one way. If you not, act different way. That's not a module. Okay? So put first your include files. Then if you need to import anything, bring the imports in there. Okay? And then declare your module. And if you need to export something, write the exports. And if you need any other declarations that need to be shared between the implementation units, put them there. So this is what you put in the interface file. And every declaration that you put in the interface file after the export declaration is seen by all the other translation units in the same modules. From the outside, only exported declarations are seen. Okay, so the interface file acts like a header file in the sense that it is automatically there for all the module units, and it only gives a portion of the view that is needed to the outside. Okay, so why are we doing this? Why are we messing up with C++? Isn't C++ already complicated? Yes, it is a very complicated language. And why are we doing this? I mean, you could make the argument that somehow we have these cataclysm coming, global warming is there, and we need to be doing green computing. Fine. But what I mean is that C++, if you're developing C++, we do too much of the same work repeatedly, and that is not good use of calorie. Okay. So we need to scale build throughput. I'm presenting here reasons why we're doing this in the reverse order of why I want to do it. Because what I've found is that faster build time talks more to most developers than I had expected. However, developer tools is something that people really envy somehow from the other language. When people are starting new projects, they will cite productivity tools in Python, Java, C# as reason not to use C++, or as a reason to migrate away from C++. And there is no reason why that should be there. There is no fundamental reason why that shouldn't be there, right? We can do that, C++, okay? If we have structure, and the structure I propose is modules. And then if you're developing at large, you really need structure in any way. This is why we're doing it. The existing code organization and linking model doesn't scale in any way, okay? Templates have to be in header files, so the link implementation details. And how we link programs, it is astounding. This is a technology that comes straight from the 70s, and somehow we haven't managed to improve over the situation. So we have header files. We include header files, right? For the compiler, including header files just means go copy and paste textually what is in that source file, bring it into this source file. It doesn't actually share anything. It is copy and paste technology, right? We all know copy and paste is bad, but that's exactly what we're telling the compiler to do. Okay, so we don't have real dependency. And the way the linking model, so when a compiler does itself produce OBJs or object files that the linker has to link, the way things work is essentially, if you're a translation unit, you think you have an idea about something over there. You just brand use some declaration. right? And the compiler says, okay, you can use that symbol. I know what the declaration is, and blah, blah, blah. And then at link time, like, where is this thing? Oh, yeah, you guys have it, so come here. But is it the right guy? I don't know. I have one. I'm just going to put it together, right? It is error-prone. It is insane how much of bugs you get there with that process. We don't have structure at the linking level, okay? And so if you have a compiler that allows you to check for ODR violations, so Clang or MSVC, and these days also GCC, they spend a lot of time, a lot of calories doing stuff that they shouldn't be doing in the first place. They're doing that only because the linking model is just not good, okay? So this is how things work. You have translation units. They're compiled separately, not just separately, but independently. They don't know anything about each other. Yes, they might include header files that are the same, but those header files are not anything other than just copy and paste, okay? So what I'm suggesting is that you have, I'll give you an example of what I'm saying here. Here you have 3 source files, 3 translation units. The first one defines a function called quant, right? It takes 2 arguments, 2 integers, and add them, the square. And the second brandishes a declaration. Oh, somewhere there is a function called quant. It takes 2 integers. I don't know what it does, but it does something and it returns an int, okay? And then that's the main source file. And then a third source file says, oh, and I have another quant, and all it does is adds the absolute values of the argument, okay? So I can construct 2 well-defined programs out of these 3 source files. If I take 1 and 2, that make a well-defined program. Similarly, if I take 2 and 3, that also makes a well-defined program. So just brandishing declaration doesn't tell you anything at all, okay? And if you build large systems, how do you keep track of the right definition, right? Some linkers will just pick the first one. Some would actually work very hard and check whether there are multiple definitions and warn you. But they don't do a lot of good work out of that. And how do you ensure that the final binary is doing the right thing? It's impossible. And header files and macros, I won't say more about that because, not good stuff. With modules, you have these kind of stuff. You have set of source files, well-defined interfaces, and it communicates through interfaces. Now, because you take symbolic dependency on components, the entire tool chain can keep track of that and enforce rigorously dependencies and check that everything is done right. So this is the new world. This is what you're going to get in C++ 20. This allows you to have, to reduce bugs, have type-safe linkage, and it works much faster because a lot of the checks that linkers, the compiler do, don't need to be done anymore. Okay, so how does this work? In 2015, I made the first public announcement effort of getting modules for C++. It was 2015, so at the time I was very ambitious. I thought that, hey, we'll get something into C++ 17. And it must be easy, right? Everybody has modules, so C++ should be easy. Okay, I learned that, yeah, you should never announce dates like that without doing a lot of stuff. So that never happened. What we got instead was a technical specification. But it was good. It focused the attention of the C++ community. So there have been a lot of chatter before 2014. David van der Voort from EDG, the template guy, right? Templates, the definite, comprehensive, whatever, that's David. He wrote an exploratory paper back in 2006 about what modules could look like. after a while, nothing happened with that. When Doug took over, he mostly worked on Clang and implementation that was designed to allow Apple to transition from C++ to Swift, right? You know the way Swift works is interpreting with C++ is that essentially you build a PCH with Clang and call that module, and then you can reuse that AST representation in Swift. That's the way things work. That's what you get when you invoke Clang with -f modules. So the timeline, this is a very simplified timeline. So in June 2014, at the Rapperswil meeting, I presented the first design. Okay, yeah, I should say something here. So when I started working on modules, Microsoft was not interested at all in a Microsoft-only extension. Remember, it used to be they will go do their own stuff, like C++ CLI, or C++ CX, or some other stuff. And they wouldn't care about these standards because, well, they are their own standards, right? What I was told explicitly by my corporate vice president was that they're not interested in Microsoft-only extensions. If you can't get this, the C++ community excited about this stuff, don't bother. That was very simple roadmap, right? So in June 2014, I presented initial design to the community. If they said no, then that would be the end of it. It turns out people were very excited about it. It was, Rapperswil, and that helped. And then CPPP happened. I had the first implementation. Then I could announce that, and it was released this November, December. People could start playing with it. And it turns out it has a lot of bugs. That's what happens when you work with a compiler that goes straight from tokens to assembly language. Until recently, that compiler, Visual C++, doesn't have AST. It still doesn't have AST. It has something called parse trees. But the way it works is the way people used to work in the 70s. You go straight from tokens to assembly code, okay? It handles templates. And the way it does that, don't ask. And so remember, with modules, you get isolation. Things are processed in isolation, then you reuse them. Well, templates don't work that way very well. There is some, information flows both ways. So people who tried the Visual C++ implementation back in 2015 were complaining because they were getting a lot of weird messages. And the reason was, well, since we didn't have ASTs anyway, we only had tokens, we couldn't do two-phase name lookup and a bunch of other stuff, and that was showing through the implementation. Anyway, we started the TS process back in February 2016. Facebook got very much interested in having modules for C++. They too didn't want Clang-only modules. They wanted something that the C++ community would be behind. And they said, well, if you being the C++ standards committee, if you guys are really serious about modules, please give us a document, something that shows that you're seriously behind it. And that document will be, create a new work item saying we are going to do modules technical specification. So at the end of that meeting in February 2016, the committee effectively produced that, asked the convener Herb Sutter to create a new work item to start doing module specification. And they also funded someone working on GCC to start doing implementation. That's actually very interesting, where here you get different companies. Some people think they're warring rivals, but they all share the same thing, which is they have this tool, this language that they want to improve because they have all similar problems, right? So that helped a lot, getting Facebook in and asking the committee, if you're serious about it, do this, otherwise go home. And the committee created technical specification, the new work item. And then I was nominated as project editor since I had the design. And working on that was really, really interesting, instructive, and time-consuming. All right. So by the end of January 2018, the committee voted out the formal technical specification. Okay, and almost a year later, like last February at the meeting in Kona, again the committee voted modules into the working draft. So this is quite recent. This is why I want to talk about it. And we are on track to put out a what we call draft international standard to national bodies to comment on. And if they all say, yeah, we're good, then we will have a standard next year that will have modules. I consider this a major milestone that will get something this big in just 5 years. Compare that to concept, for example, which I've been working since 2002 or 2003. We will get it also in 2020, but it took 17 years, okay? And it is a big, major feature, but I maintain that modules are probably the biggest, the most impactful feature since classes, because this is an abstraction that gives you boundary that you can name. Concepts are also abstraction, but not in the same way. Modules are closer to the abstraction that classes give you than concept. And we managed to get this done in 5 years, thanks to having at least 3 different implementations. Okay, we got exported templates back in '98. Had no implementation at the time that was voted into the standard, right? Here, we know what will work and what will not work. And by the time that we put out the standard, you will have full implementation that you can play with. You already have partial implementation. So this is, the way we are doing this is very, very different from how we used to do things, okay? So this is really big. So, you know, the module TS is out there. Now it is too late to comment on it, but it contains the original design and everything else, in case you're interested. So, like I said, at the Kona meeting, we voted to have modules into the working draft. So we took the technical specifications, and to make any progress, we needed to address concerns from Google, who had concerns about the design choices and wanted something additional. And then there were other feedback like, you can't really have module as keywords. That was coming from people who do graphics, and they're using some library like Cycle library that apparently uses modules and imports as function names or parameter names. And they say, well, we really love modules. We can't take it if module or import is a keyword. So the Atom proposal, Atom here means another take on modules, from Google, essentially proposed a new way to transition from header files to modules, okay? And the module TS had some severe restrictions on what interfaces are, and that was relaxed. And because modules are new constructs and build systems need to know about them, we needed to have some structure to the source file. So we introduced the notion of preamble. I'll get into those on the next slide. So header unit. So essentially the way you think about them is as a formalization of precompiled headers, right? If you have a big header file, or have a bunch of include, you put all the include in one header file. You know that this is used, repeatedly. Almost all compilers offer some extensions that allow you to kind of pre-compile those includes and then try to reuse them in source files. Depending on the implementation, they may be flexible or not at all. So there is an implementation GCC, one in Visual C++, one in Clang, and other compilers, and so forth. So the GCC implementation and the Microsoft implementation are very similar in the sense that to make reuse go faster, all they do is they dump the state of the compiler at the end of pre-processing your include. So it is really memory dump of the process. And when you're reusing, they just reload the state. So there is no tokenization. There is no parsing done. Right? That has never been done. It is fast. It is extremely hard to beat in terms of speed. At the same time, it is extremely inflexible. What it means is that even if you're developing on a different machine, same architecture, it is very difficult to actually reuse, just copy over your PCH onto a different machine and reuse it. The same goes for Microsoft Compiler. Microsoft Compiler is even worse than that, right? You can't even, if you're building on the same machine and you have different projects, and they all happen to have textually the same PCH, you can't share the PCH between a project, at least until a few months ago, right? And Clang has a different approach to PCH, which is instead of dumping memory onto disk, they will serialize the data structures that the compiler needs in some structured form, which I think is a very intelligent way of handling stuff. That allows you to actually copy things around and share and so forth. That notion of precompiled header is an existing technology. It is just that implementation differs. So it makes sense to want to standardize in some form. Now, it is existing practice, but the problem is that the syntax, the existing syntax to use that today differs from compiler to compiler, right? GCC has one way of doing it. You can only have one PCH. Microsoft has another way. You can pragmas or not pragmas. You know, the syntax is very bizarre. And worse, the way it checks for reuse of PCH, it just skips a bunch of tokens until it says the includes and just reuse that. So it means that you can have arbitrary tokens before that includes. It will work, right? And the way I used to characterize it is that MSVC can take any arbitrary token and make an executable out of it. Okay, it doesn't have to make sense. It can make an executable out of it. And the Clang has something different. Now, how do you go from there to this standard? So the way you go from there to this standard is this. So I showed this syntax earlier. I'm coming back to it again. So normally, you'll have hash includes outstream. Here, we have the import keywords, right? I'm going to say keyword, but actually context-sensitive keywords. And then you have header name. You can also use the quote name. Now, the thing you have to understand is that because this is not hash something, it is supposed to be fundamentally understood only by the parser, right? The preprocessor used to be, you bring things in and it turns true tokens, macro expand stuff, and then move on, right? And then the parser comes after. Here, it is happening at the parser level. That is the idea. In practice, and the way it is specified, it is a little bit more complicated. The reason is that the header could actually export some macros, right? The header could actually define some macros that are expected to be used later, right? For that to work, we have to inform the preprocessor that the word import is special. If you find import, a header, go locate that header, bring in all the macros. Don't do anything else. and then continue and tell the parser later to just bring in whatever is needed. This is a hybrid between header and real modules. What I call real modules is real modules, they are not understood by the processor in any form, right? That capability is needed because today, many of existing headers define macros as a way of communicating. If you're using Qt, for example, it has Q objects, a bunch of other stuff. Like mock doesn't work if you don't have the right Q object, whatever they are, at the right place. And we want to allow people to reuse those kinds of headers and at the same time benefit from the speed up that you get from modules. So this is it's a service to the C++ developers. It is a nightmare for compiler writers, and even to specify, right? So I didn't put the nightmares on the slide because I thought that is mostly kind of code porn, but because it is context sensitive, you could actually use import as function parameter. In that case, it would not be special in any form. And that means you can also have a class called import or a class template called import that you can instantiate over an int. And then if you say import bracket int x, well, that is not actually import a header file called int. It is supposed to be the template. Yeah, so it gets very complicated. I'm not going into details there. Using header units, the way it is specified here, also means you have a slightly more complication in your build system. So you first need to compute, to build the precompiled header for ostream and string. That's done once, right? And then put that as a dependency for this file, that PCH as a dependency for the file date.ixx. The same goes for the code on the right side where you have ostream and other stuff. You also need to create the PCH for that, right? So if you have a huge code base like you have at Microsoft or Google or Facebook, this saves time. If you're just doing a quick demo, it doesn't save you much because there is not much reuse here, right? Everything is used at most once, so there is no reuse, and just your ordinary include will just do fine. Okay, so this is something that you need to be aware of when you're adopting modules, and especially header units, that they create an additional dependency in terms of PCHs. Now, when a parser sees the import, it asks, where is the PCH corresponding to this header? And then we'll look at it and use that PCH instead of the context of the header file. And that is where the speed up comes in. Okay. We also specify the modules such that if you export something, that something is not brought in by default. It's only when you use it that the compiler says, oh, I know where that is, I'll bring in a definition, right? So, in C++, we have this guiding principle. You don't pay for what you don't use, right? With the includes model, that is not true. If you include IOStream and you only use cout, you're also paying for cin, which you're not using, right? With this model, header units and modules in general, the declarations are located on demand, not right up front. This is fundamental. This is why you get the speed up that you get. Okay. The implication for this is also that your existing build systems, you'll have to modify them in some form to make this work. And we all know how fun it is to modify an existing build system. I don't know how MS Build works. They're forcing me to make it work, and I'm busy trying to get experts' help to make it work. It is no fun, but it is necessary. And the implication is that people who build things like make, CMake, MS Build, Ninja, and all of that, they will have the fun part of making this work for you. Okay, that is the expectation. And I'll get that shortly. How am I doing on time? One more second. Okay, thank you. Yeah, there is another, so if you look at the, the major additions, we have header units. Now I want to talk about module partitions. The module TS I put this restriction that a module can have only one single source file that contains the exports, right? So I think you all see the, the flaw right away, right? That means you're going to have a gigantic file that contains all the exports for your modules. Oh, I should say right away that the way we intend you to use modules in C++, it is not one module per class. I mean, if you want to do that, yes, go ahead. But you'll find out that you have a lot of modules, right? And if you have dependencies, you're just going to create a bunch of synchronization nodes in your build system, and it's not sure it's going to go faster. So what you want is cluster, right? Remember, modules are for development at large scale, okay? So if you have a large scale modules for large, and then you have only one single source file to create your export, like, you know, I'm not going to do that as developers. Like, no, this is insane. I put that restriction in there because I didn't want the committee to spend 2 years trying to figure out how to do this right. For me, that was just detail. An important detail, but detail. I wanted the committee to focus on how do we get this thing done. That problem, we'll solve it later. And we solve it. We actually solve it in less than 6 months. But I don't think we'll have spent 6 months if it was there from the beginning. I know that because I had a lot of suggestions about how to do it. And it's like, it's not that I don't know how to do it. It's just that I don't want to do it now because it is not the most important thing. Most important thing is to figure out how the whole thing is supposed to work. Name lookup, I didn't want to have new rules. How do we make sure that we don't add new rules? Because we don't need to complicate the whole stuff. Okay, so the module partitions, they're just ways of saying, I have this module interface. And the declarations are split over several source files that I want the system to think as if they're just small modules that I'm putting together. Okay, so you have the name of your module, colon, the name of the partition. So here, for example, I say export module binary tree. So I have a module binary tree, and if I want that partition to contain only the structure for definition of a of data structure, now I'll just put it there. And then I have another partition that contains all the algos. And I will have a single source file that will export all of those. The way you can think of it, if you want to have the analogy with header files, is that you have a master header file. Like, let's say Qt. I have Qt core that contains that just include a bunch of other subcomponents, right? So the way you think of module partitions are that they're just equivalent of smaller header files that are included in a master header file so that you can develop your abstractions in the source file the way you want them. But you still need one place where you re-export everything together. So in a sense, it is emulating header files, but I think that any other solution to this would have required a fundamental change to C++, one that the community and the committee was not ready to embrace. For example, we could just have decided that you split your interface file over several source files, and somehow the compiler knows how to find them. Somehow. If you're familiar with C#, that's the way it works, right? And that's wonderful. The only problem is that in C++, you cannot parse C++, I'm talking about parsing, if you cannot do, at the same time as you're parsing, template instantiation, overload resolution, spinning, and a bunch of other stuff, right? And if I'm using vector of t, and I say vector of t colon colon iterator, or vector of int colon colon iterator, right there, I need to go find the definition for the class vector, instantiate, and say, oh, colon colon iterator is a type, then I can do this. Before proceeding, right, it's insane. You cannot, it's worse than that. You cannot even lex correctly without doing semantics analysis. Example, you have a template. Let's say vector of int, and then you close with bracket, and no space between the brackets. So that's the like, shift operator. For that to work, I need to know that vector is actually a template. So I need to go and find the declaration for vector and say, oh, it is a template. Okay, now I have to magically separate that shift operator into 2 tokens, right? So you cannot even lex correctly C++ without doing semantic analysis. Okay? This is fun stuff for compiler writers. Okay, so to get the model that C# has would have required a fundamental change to how C++ works. The community is not ready for that, and most certainly the compiler writers are not. We're not ready for that. So we get this model, which I believe is a good compromise between the ideal and where we are. Okay. So this is an example of how module partitions work. So imagine that I have a module called binary search tree. And what it is doing is to re-exporting. The way you re-export modules is export imports, okay? This was not my choice. My choice was export modules, but the compiler writer union banded against me and wanted export imports. And if you're from the US, you also know what that means, right? Export import bank, okay. So this is the syntax you have. And binary tree colon data means that I have it should be binary search tree. Right? So this is what happens when you have a PowerPoint code and that hasn't been type checked by the compiler. Actually, binary search tree data because it has to be the same module name, and then you only have the semicolon. I'll fix these before sending it to you. Sorry about that. And then you have the 2 partitions, right? So each partition can also export things that it wants. That defines that. You can think of the module partitions as some kind of sub-module, but it's not like a sub-module, but right? And they are all parts of the same module. So this is the way things work. The fact that you have that master module unit that re-export everything is the compromise that I was talking about. The only way to avoid this is somehow says that, the compiler has to know how to use these things. While it is compiling, it has to go and find this stuff and then compile it before continuing declaration. That's just a nightmare. It's too complex to work. It is not that the technology doesn't exist. It exists, just it's difficult. If you're using the Visual Studio IDE, for example, you can see that you can have a function, a declaration, that has some type, and then you can define the type later, and then somehow the IDE links those 2 things because it can do that stuff. We call it tag parsing. The technology exists. It is just that it's not widely used, and it includes support for it in a build system will be a real challenge. Okay, so we can't have that C# nicety in C++. And I didn't really just want to copy some other language stuff. Okay, this thing I think is important. When to use include and when to use header unit. So include, we are all familiar. It's copy and paste, and we have been doing that for the last 40 years, and we know how it works, okay? So again, if you look at the source code, now module semicolon, you include things that you know for sure you want to use. So here, oops, what am I doing? No, sorry. Okay. So here, I know for sure I want a stream. That is exactly what I need. Okay. So here, when the compiler sees OStream, it goes, okay, it is in that header file that is already included. And then what it will do is that it would save on disk somehow the declaration for OStream. And only that, and nothing else. So when I import calendar date here, the compiler doesn't bring in all the stuff in there. No. Only what is used here, string and OStream. That is all it needs to do in this include model. This is what you do when you know exactly what you want from a header file. Furthermore, that header file is so big that if you're building stuff at scale, you don't want it to be replicated all the time, right? Concrete example so this is a place where I was informed by the problem that my employer had. It is building Windows. Okay, so there is some executable components in Windows. When you build it, you get an executable. It is about, let's say, 500K executable. But the whole process to build it, the PCHs that are built, you get 1.5 terabytes of PCH. Just the build artifact, 1.5 terabytes. Okay? Now, you have about, let's say, 5,000 engineers working on Windows source code base. You know, these numbers, you can actually find them on the web because we had some blog posts about them. And imagine they submit a pull request. So when you submit a pull request, it triggers a build in lab. Okay, not all 5,000 engineers are going to submit a pull request in a single day. Let's say a tenth of them do. So you multiply 1.5 terabyte by 500. That's a lot. Now, every night, we actually have builds of the system. For regulatory purposes, you know, government asking to save stuff, the builds have to be archived every single night for a certain amount of months. Think about how much disk space that is. I'm not joking. The numbers on the internet. So this is a real problem, and there is a specific department team in the Windows division then whose purpose is predict how much of disk space we need to buy, that kind of stuff. Okay, so saving on the PCH is fundamental. About a few months ago, they have adopted a different strategy, which is that they have some scripts that go around and delete PCHs that are needed just to reduce things. If you submit a pull request and it makes things excess an amount, your build fails. Sorry. Try again. Okay. So being efficient is fundamental because it saves money. Okay. So this is why we have this model where you bring in only the things that you need. The other model is the header unit. So the header unit here, what it does is, I don't really know what will come out, so save everything in case I might need it. Sometimes that is what you need, especially if you have very template-heavy clever codes that use FINE. If you have the right amount, that declaration have slightly less than 3, it's the other declaration. You don't know what you're going to get. So you put all declarations there, you save it on disk, and you cross your fingers, right? So you use this model when you don't actually know exactly what you want. It might be this or it might be that. It's that, Schrodinger's cat. It's dead or alive. No. You need both, but you have to understand what your requirements are in order to use this properly. And I think this is very fundamental for efficient use of modules. There are people who want to tell people, do this all the time. You have to understand the implications. If you're not constrained by disk space, that kind of stuff, go for it. If you're very conscious, you know exactly what you want, you don't really want to do that. Okay, so that is my advice. Use header includes, especially if you want to provide a project a modular view, right? And use header units if your header file is already well structured, right? C-assert or assert.h is not something to consider as a header unit because it behaves one way, the other depending on how macros, which macros is defined. So it's not modular in any form. Windows.h, it is not modular. When I started, I was hoping that I'll work with the Windows division and get some modularization out of it. We spent months with the best engineers, and we came to the conclusion, we might do something, but this header file has been around for so long and supports so weird combinations of stuff that it's not worth it. So don't use Windows.h for header unit, unless you know exactly what you want, which is I have no min-max, or lean and mean, and that's the only thing I'm using in my entire project. Then build your PCH with that and pray. Right. So this is a real change to a fundamental change to how we write code, how we develop, and how we build. And of course, that means implication to the C++ ecosystem. People providing build systems, Make, GNU-Make, CMake, they are concerned, and thankfully they are also involved in this standardization. So we're sorting things out. My employer sells an IDE, Visual Studio, and there's a difference in working on that. I work on the front end and back end, and people working on the IntelliSense, they have other needs. We talk, but I'm making their lives harder. Okay. So education materials, now we have to produce, we have to update our educated books to the new world. And really, this is bringing C++, what I'll call, into the 21st century, especially when we have the semantics hour developer tools that come with it. Like if you want to produce binding to other language, what people call foreign function interface or whatever it is much easier now with modules than it is with anything else. Because when you compile a module, you have to save something on disk, which is the binary representation of things that is exported or not. If you look at it very carefully, you no longer need a C++ compiler to actually make sense of that binary format, okay? It could just be a very dumb binary parser that gets that done, and that's usually much cheaper than writing a C++ compiler or parser. There are people who do that for a living. EDG, they write the best parser on the planet, but they're professionals. They have been doing that for 30 years, okay? And because the ecosystem is so impacted, there have been some concerns, and I think Corentin, was among the people who, hey, look here, you're breaking my stuff. and currently is among people who are making my heart much harder, my life much harder. And now we have a working group called Tooling Group, and at the last meeting in Kona, we decided that we will publish a technical report, primarily for tool builders, to say this is how you handle modules. Like if I write binary search tree colon data, how does the compiler find that? How does the build system find that? And how you map that to a real source file, right? There are a lot of opinions about how that should be done. And you know, I'm quite very happy that the community is coming together to embrace this thing and solve these problems. This is really, really good stuff. I've never seen it before. So I'm really happy about it. I also think that this is the enabling technology, something that we haven't done before, we haven't seen before in the C++ community. So here is why. I'm not going to give you a lot of specifics here, but I do promise that by the end of this year, I'll publish more material about this. Imagine, so what is going on is that any good C++ compiler, when it processes the module interface, is going to save on disk something that says, this is what is exported in some form, okay? I don't think it's going to be memory dump because we all want to share stuff, right? I also think that it will be really disastrous for the C++ community if on a given platform, Linux, Unix, Windows, for a given platform, you have N compilers, GCC, Clang, EDG, MSVC. Each has their own format that they don't want to have anything in common with. It don't work in isolation, in a silo. It'll be disastrous to the community. I know that today, there's people saying, oh, no, I don't want to, I know how to do that stuff for my compiler. I can define a more efficient representation if I don't have to care about yours. I was like, great, but if we get together, we list our problems, how we do stuff, and we come to agreement on a common representation, I suspect we can do a much better work, right? So this is a challenge I'm putting to the community, and I will share more about this by the end of the year. And it will also be if we don't do this, it will be really a missed opportunity. It will be, I can't understand it. And the community, the C++ community will not forgive the C++ committee if it doesn't take this opportunity. This once-in-a-lifetime opportunity to do something much better than what we have today. So to get this done, I think the binary format that's going to be, what's going to be saved on disk is going to represent all of C++. Because these days, you have things like declare type that can take an expression. An expression can have a lambda. And lambda is, well, I can put a class there. And now a lambda can be a template. So you're going to have entire C++ represented there. Okay? Once you start representing entire C++ in a structured form, why don't you want to share that with the community? One of the things that Java has, which is really great, is it has this thing called Java class file format that is documented. People can write tools against it. People can even write different language that target that format. And it runs on the same JVM, right? You have Kotlin, right? It's fantastic language. Scala is fantastic. A bunch of other stuff. Even old languages like Lisp, they have an implementation on the JVM, right? If you really want to make C++ a good player, I personally believe that the toolset developer community want to embrace this opportunity to define formally what we call the abstract C++ machine and representation, so that even people doing different languages can target. It becomes much easier to interpret with C++ than what we do today by Swig or whatever it is. Okay. So I have done some work on this about 15 years ago when I was at A&M with Bjarne Strostrup, where we developed a complete representation of C++, or C++11. And I haven't updated this since then, but I know that the update doesn't require a lot because the format that the Microsoft compiler is using is directly based on the ideas in the IPR. Okay, and I know it is possible because I've done that work. And when I did that work, I had GCC generate that format, and I had two students who generated the same thing from Clang. So I know that is possible. It is not a matter of skill. It is a matter of wills, whether people are willing to do it, right? This is not a matter of skills. I'm putting this challenge to the tools developers community to serve the C++ community. We are more than 5 million developers, right? And the number of people who write C++ compilers, I can fit them in a tenth of this room, right? And if you go to the standards committee, the core group is usually a small, they are locked in a small room, okay? Those are the people on the planet who can do this stuff. And they should just embrace the challenge and make the lives of 5 billion developers much better. I'm getting to the end. What I want you to do is that you try the ongoing implementations. If you're on Unix or Linux, go take GCC or Clang, okay? Have link there, and GCC, it's on a development branch. I'm hoping that by the end of this year, they move that into main trunk so that next year we get GCC 10 that has module support. That's my hope. I'm not working on GCC anymore, but I do hope that's what happens. Clang has an implementation in the main compiler with a switch minus F modules TS. And MSVC, from the beginning, has had implementation in the main compiler. The latest version is better. And if you have comments, you can contact me or your representative on the C++ committee, or you can directly send your feedback to either modules@iocpp.org, and if you have suggestions about tooling, then you can also send feedback to tooling@iocpp.org. And I would love to get feedback from you. This is what I want you to do. Now I'm ready for questions.
Hi, thanks for the talk. Do you have some recommendation what to watch out for when we have our existing code base nowadays, apart from the rule of the include and try to keep the use of macros at a minimum? Some recommendation what we can watch out for in our code base today, even if we cannot use modules yet.
Yeah. Okay. The recommendation I have, or that you have?
No, what you have.
Oh yeah. So that was on my slide, one of the slides earlier. Sorry. So the idea is to have the include first, and then the imports.
Yes.
That
I got. Apart from that?
I'm sorry?
Apart from that, something to watch out for? Or that's mostly it?
Mostly it. So the imports gives you the modules benefit, right? So any macro that you define in the include is not going to affect the contents of the import. Okay. If you do use header unit, then the macros that come there might affect, right? But if you use proper modules, the order of imports is no longer material. But one of the problems we have existing include today is that you have to include the right order. Mm-hmm. Otherwise, you get surprises. You don't get that with modules anymore, right?
Thank
you. And the recommendation is very simple. Include, imports, and declaration. It's very simple.
Okay, great. Thanks.
there's one point I did not remember exactly. If in a module you import a header unit, let's say for example IOStream, and you import this module in another code, will you have access to the stuff that comes from IOStream? Or is it isolated? Is it transitive input?
Transitive. So header units work essentially like headers. So if you get any other includes, so remember the header units are just header, so you get everything in there. So if that header has some imports, you get that too, right? But if you have modules, if you say module imports binary search tree or something, that translation unit is the only one that gets things there. It is not transitive. If you want to re-export, then you say export import binary search tree. But if you use header unit, then anything that's in there gets to you. But if you want to make that available to anybody else, then you have to prefix that with export. So the difference between that and a header file is that there is no transitivity at the point of import. But from the source, you can get things that are transitive, if it is header units.
Hey, nice talk. You mentioned build system support at some point. If I want to try today, let's say I have a CMake project, and I want to try to use modules, how is it going to work? Because I guess there is some module discovery thing that needs to run or exist. Is there support for that, or?
Excellent question. As a matter of fact, one of the people working on CMake, Ben Booker from Kitware, is actively participating in this. And he has patches for CMake, that is the discovery of module dependencies, and that requires some patch to GCC that he also applied to GCC. So today, GCC and CMake work beautifully to get module discovery, dependency discovery. Unfortunately, you don't have anything like that for MSVC or Clang yet, but that's only a matter of time. Thanks.
Hi, I got the impression that I was told that if you use a module, it's virtually free for you.
It's virtually?
Free to
Yes.
use. And if you are going to standardize standard format of it, you need to parse it and read it. How do you propose to make it work?
Oh, okay. So if I understand the question correctly, is import of module essentially free? True. And if I'm going to propose some kind of standard binary format, and how is that going to work? Okay. It is very simple. When you import a module, what you're telling the compiler is, well, I have these global symbols defined in that file. That's all it is. When the compiler sees the use of a name in the importing translation unit, it says, do I know anything about stud, for example, std, for example, and all the imported modules say, oh yeah, I've seen something named namespace. And then they go and say, okay, oh yeah, go and bring in top-level declarations. And that is parsing on demand, right? And that is very simple stuff to do. And the binary parsing is also extremely simple. Okay, the simplicity is just, to give you an example of how simple it is. I could get this done in the Visual C++ compiler in less time that it took me to actually implement some other stuff related to templates.
Just curious, how does it combine with the already existing Microsoft extension to import and export from or to a DLL?
Oh, so the module construct as presented here is completely independent from the notion of DLL, which is some people also call modules, which is really at the linker level. One of the things that you get here is when you have declspec export, declspec import, the the approach I took was that if you're going to mark a symbol as DECL export, for example, you most likely also want that symbol to be known to the outside world. So you're just going to use the C++ keyword export. And then you say DECL spec export that function, for example. On the import side, you don't need to mark anything as DECL spec import, right? Today, what people have to do is that they have to say DECL spec export, DECL spec import, and they never know exactly when to say one or the other. And then you have this macro DLL export, and then get people confused. The implementation takes care of that. The only thing you need to do is to say DECL spec export, and on the import side, it automatically takes care of the rest.
Okay, great.
And
so we won't have to duplicate the export.
That's
Okay,
right,
that's
yeah.
great. Thanks.
Yeah. Excellent question.
There's something I still don't know about modules is how big should they be? For example, if I have to modelize the standard library, should it be one module for vector, or one module for all containers, or just one module for the whole STL? Sorry, for the whole standard library.
Excellent question. So at the same time as I was proposing the core language facility, I also proposed, people are going to use module. This is how I believe people should view modules. That is not going to get into the standard because the library group was very nervous. Oh, this is coming late and we don't have time to do it and all of that. But the paper, I forgot to put the link on the slides. I could add it and when I shared my principles are very simple. The first thing is that it will be absurd to have one-to-one correspondence between headers and modules. Today, the standard library headers are optimized for what people believe minimize declarations in headers. Now that modules are essentially free, we can focus our attention to logical organization, right? This is what I said earlier, that modules, for me, it is to solve architectural problems. So the principles I used, for example, was that you have things that I consider fundamental, core, like you'll find them in freestanding, like embedded systems. That's just one thing. I call them fundamental. And then you have things like the STL, strings, algorithm, all of that. It just come together. It is rare that you're going to use vector of int, and then you're not going to use the iterator. So instead of including iterator, then vector, just put everything together. Similarly, if you're using container, it is very likely that you're going to use some of the algorithm. So instead of separating the algorithm from the container, just put everything together. So I proposed about 5 different modules for the entire standard library. And furthermore, most beginners don't know exactly which one to include. So go for just a big module that contains everything. Import stood, move on. Because modules are very cheap to import. Of course, people say, yeah, but when you do that, then people become careless. Maybe, but if the problem you're trying to solve is about architectural problems, then you're focusing on logical composition, right? That's my answer. I know that today you have also principles like you have one header file per class, right? I don't recommend to have one module per class. I recommend to look at your component and say, what are the logical things in there, and group them like that. Okay, yeah, apparently we exhausted all questions. Thank you very much for coming.